All right, guys, so this is our last new material for piecewise functions. After this lesson, we will have a review lesson, and then you will have your assessment on piecewise functions. All right, so on the left, you can see your starter from yesterday, and I asked you, which one do you think is a continuous function? Why do you think that one's continuous? And you could choose more than one. So before I give you the actual answer, I'm going to scroll down here and show you these graphs. So on the left, these are all examples of continuous functions. And on the right, these are examples of discontinuous or non-continuous functions. So based on these examples, do you think that what you chose yesterday was correct? Well, if you chose graph 4, you were correct. So let's actually talk about what makes a function continuous versus discontinuous. All right. So now I'm letting you know that these are informal definitions. You will learn the formal definition of continuity in calculus when you take it next year. But for now, these definitions will work for us. All right, so for a continuous function, basically, this is a function for which the graph has no breaks in it. So a function for which, let me fix that, for which the graph has no breaks. And actually, one of you defined it very well yesterday. There are no jumps, no holes, and no vertical asymptotes. There can be other kinds of asymptotes, but no vertical ones. These three things, jumps, holes, and asymptotes, these are the three kinds of discontinuities. So if we have a discontinuity, of course, we cannot have a continuous function. So a function which the graph has no breaks, and that means no jumps, no holes, no vertical asymptotes. Some of you yesterday also defined continuity in another way, which was another very good informal definition. Basically, you can draw the graph without lifting your pencil. So again, you can completely draw the graph without lifting a pencil. All right, so again, informal definitions, you will learn the formal one in calculus next year for continuity. So of course, a discontinuous function is going to be the opposite of this. It is a function for which the graph has jumps, holes, or vertical asymptotes. So it has breaks. All right, but what do these mean? What are jumps, holes, and vertical asymptotes? So I'm going to draw some examples down under discontinuity. You have some continuous examples at the end of this packet. But a jump, for example, this is when the graph literally stops and then moves somewhere else. So we just learned about a kind of piecewise function that does this, and that is a step function. So remember, a step function, you have a value and then it literally jumps up to another value. So those are jumps. Holes is when there's an open circle, basically. So if you have some sort of graph and there's an open circle and then the graph goes somewhere else, this is a jump with a hole. Though more typically you're going to see a hole like something like graph 2 from yesterday, where there's just a random hole in the middle. And then of course no vertical asymptotes. So we can't have anything like, let's say this, because there would be an asymptote right there. All right, so now you know what continuous and discontinuous functions are. Let's do some problems. So let's look at these two graphs. What do we notice about these two graphs? What's the same versus what's different? And I know that the axes are a little bit off, but pretend that they're the same. So hopefully you notice that these graphs are actually basically the same. Like this hole is at 1, -2. This one's at 1, -2. Both of these lines pass through the origin. These are actually the same line, but there is one difference, and that is this dot over here on graph B. So these graphs nearly the same, except for the dot or the point on graph B it's at 1, 1, I think. Yes, 1, 1. All right, so let's look at the kinds of discontinuities these graphs have. So number 1, and let me erase the markings I have on here. Remember, we learned about 3 kinds of discontinuities here: jumps, holes, and vertical asymptotes. So graph A, there's no jump because there's not a place where a value suddenly jumps to a different place. There is, however, the hole, this hole right here. And there are no vertical asymptotes that we can see. So graph A has a hole. All right, graph B is the discontinuity that sometimes gets confusing, because when we think, oh, it's a hole, right? Because it's got this hole here and it doesn't really jump around, except this is actually another version of a jump. So whenever you have a hole, but the value is somewhere else, the value has basically jumped somewhere else, this is actually a jump. So graph B has a jump discontinuity. All right, the domain of each graph. So let's think about x values. Graph A, we had that hole, and there was no other dot, remember? So basically, this graph exists everywhere except where this hole is. So basically, for graph A, your domain is everything except x equals 1. So x does not equal 1, which you can also write as -infinity. Like x, sorry, hold on, let me change that. X is less than -1, or x is greater than -1. So you can write it these two ways. Either one is good. Now graph B, remember, was different slightly because it had the point over here. So there is actually a value at x equals 1. And the only other thing we have to worry about in this domain is the hole. But the value here takes care of that hole. So we actually have a value everywhere. So for graph B, the domain is -infinity to infinity, or all real numbers. All right, so now let's write the equations of these graphs. For A, now remember, both graphs, basically, they look the same. They're both they're both basically lines, and they would be lines if it wasn't for this hole. So for graph A, you can actually pretty much write the equation like that. The equation of this graph, the slope is -2 if you count it. So -2x, the y-intercept is 0. This is the equation of the graph everywhere except x equals 1. So you could write f of x equals -2x plus 0 when x does not equal 1. Otherwise, that equation works. All right, so graph B, now we said it's basically the same, so we can actually write that as well. -2x plus 0 when x does not equal 1. But something does happen when x equals 1. So let's take a look up here. When x equals 1, we have this black dot, and that has a value of 1. So when x does equal 1, the function equals 1. And this is actually a different kind of piecewise function. Whenever you have a jump, it is a piecewise function because there's the part that's, like regular, and then there is the part that got jumped to, which is in this case the 1. All right, let's do another example on the next page. Oopsie. All right, so example number 1. This is an example that we have seen before. What kind of function is this? And this is the very first function we saw when we did piecewise functions. So this is a piecewise function. Now, is this function continuous or discontinuous? And how do we know? Now, if we look back at our definition, a continuous function has no jumps, no holes, no vertical asymptotes, and it can be drawn without lifting up your pencil. So let's see if that's true. Do we see any jumps in this graph? Anywhere that either the value just suddenly changes, or there might be a hole with a value somewhere else? And no, there's none of that. Do we see any holes? We don't see any holes either. Do we see any vertical asymptotes? Also no vertical asymptotes. And if I had to draw this, if I wanted to start at the very left of this graph, I could draw it without ever lifting up my pencil. So either one of those reasons are fine. No jumps, holes, or vertical asymptotes. And if you want to shorten vertical asymptotes, you could just write VA for vertical asymptote. So this is a definition I want you to use for now. No jumps, holes, or vertical asymptotes. And then again, in calculus next year, you will learn the formal definition. All right, so let's just do one more example while we still have a little time. So this is a step function. I've already written it, and you can see that is a step because these lines form like the steps of a staircase. So yay, step function. All right, and all I'm gonna do, because I have very little time left for this video, is I'm not gonna write the equation, but is this a continuous or discontinuous function? And how do we know? So obviously we can see that this is a discontinuous function. We definitely are not going to be able to draw it without lifting our pencil. But mathematically, does it have a hole? Does it have a jump? Or does it have a vertical asymptote? And this one, the very specific kind of discontinuity has is the jump, because we can see these values jump to different places. So discontinuous because there are jumps. All right, so make sure you do part B, write your equation, and then please do the rest of this packet. They're very short questions, so you should have time to finish it. All right, email me if you have any questions, and stay safe.